All right, the alternating series test also gives us a little bit about what is conditional and absolute convergence. So the alternating series test says that if you have some series where you have an alternating component, okay, where b sub n is decreasing, right? So the b sub n term is always greater than the next one. So b sub n is decreasing and goes to 0. Okay, then you know that this series has to converge. Has to converge. So let's look at some examples here. If I have alternating series negative 1 to the n plus 1 over n squared. Well, 1 over n squared, if I take the limit as n goes to infinity of that, I get 0. It is always 1 over n squared is always a decreasing term, meaning 1 over n squared is bigger than 1 over n plus 1 squared. And you can show that, okay? If you could show just with cross multiplication, really, n plus 1 squared greater than or equal to n squared, okay, or the reciprocal rule, and you could flip the sign. So therefore, I know this converges by alternating series. Okay. Let's look at this second one. So this has an alternating piece, but let's look at the limit as n goes to infinity of n over n plus 1. Well, that limit is going to end up being 1. So even though this is a decreasing function, limit is going to track to 1, so this diverges. But it's important to note that it doesn't diverge because of the alternating series test. It actually diverges because of the nth term divergence test, right? Because we should always check that first. So you should always check if your a sub n goes to 0 or not, because if it doesn't, then the whole thing diverges, right? All right, so then this brings us to the thought of absolute convergence versus conditional convergence. Because if you look at something like 1 over n, well, 1 over n does not converge, right? We know that the harmonic series, 1 over n, does not converge, but if you put in that alternating piece, now it does, okay? So we would call that conditional convergence because it only converges because of that alternating series piece. It doesn't converge on its own. Now, if you know that the absolute value of the of an alternating series does converge, then the without the absolute value bars should also converge. Okay, so what does that mean? Let's look at our examples here. So I can look at this right here. The series 1 over 3n plus 1 would diverge, okay? The reason is you could use it comparison to 1 over n. N is always less than 3n plus 1. So 1 over n is going to be bigger than. Just kidding, you can't do that. That is not true. All right, let's do limit comparison. When I divide by 1 over n, that's the same thing as multiplying by n over 1. This ends up going to 1/3, which isn't 0. So these either both converge or both diverge, so that diverges, okay? What does that mean? Well, that means that because I do have this limit as n goes to infinity of 1 over 3n plus 1 equals 0, and each term other way, right? Needs to be decreasing. There we go. Okay, that's also true. because of that alternating piece, this does converge by alternating series test. But because it only converges because of the alternating piece, we say that it converges conditionally. Okay, only because it's alternating. All right, let's look at this cosine function. This is very, very interesting. I'm going to erase all this work, okay, and then I'm going to change my color here so you can see. So think about the cosine graph. The cosine graph is always bounded above by 1 and bounded below by -1, right? And so I can say that the absolute value of cosine n over n squared is less than or equal to 1 over n squared. Because cosine is bounded above and below by -1 and 1, and so I can say that this is true. Now, I know that 1 over root n converges, and so that means that this series also converges. Well, if this series converges, okay, with the absolute values, then even without the absolute values, that has to be a convergent series. Okay, and not only that, it must converge absolutely.